I'll give you an example here. So consider V, some vector field in R2. So this is two functions, function of x and y. And I have another vector field C and D. Again, these are functions of x and y. This is on R2. Such that they match on the x-axis. So on y equals 0, the x-axis, we have V equals to W equals to 1 and 0. So it's just pointing toward the x-axis, along the x-axis. So here is the picture. This is x and this is y. So on the x-axis, V is pointing along the x-axis. So this is V. But outside of the x-axis, it's doing something else. The same for W. W also on the x-axis, it matches V, so they are aligned with each other. Outside, they're doing something else. Maybe this guy here is constant, but here is doing like that. Okay? The same for V, maybe it's actually the other way around, or anything else. But on the x-axis, they match. Okay. Now, consider any other vector. Consider any vector, say Z. Say Z is 0, 1. Okay? And I'm asking the following very legitimate question. How Z changes along the x-axis? Please give me this quantity. What's the rate of change of Z along the x-axis? Well, we know the answer. What's the answer? Z is actually constant, so the answer is 0, right? So what is the Euclidean answer and what is our answer? What's the Euclidean answer? The Euclidean answer is pick any vector along the x-axis, right? Which is V or W, it doesn't matter, or any other vector, right? And do this, nabla Z, the rate of change of Z in the direction of V or W. If you do this, so differentiate Z, Z is constant, so you get 0 here, dotted with any vector, you will get the 0 there, right? Okay? In the direction of the x-axis. Here for Lie brackets, let's compute the Lie derivative of Z. Here is, let's make it like this. Lie derivative of Z with respect to V, Lie derivative of Z with respect to W. What are these guys? Well, remember this is partial Z, partial Q's times V minus the other way around. So actually here there is no change. This will give you, differentiate the components of V. So this is negative A, Y, negative B, Y. Partial A, partial Y, partial B, partial Y. Here is the other way around. Will give you CY and DY. And obviously these are not equal in general. So I pick a vector along the x-axis, I compute the Lie derivative of my vector along that vector, any vector along the x-axis, and the result is not different, the result is not the same. So this is not a well-defined way to define directional derivatives. The Lie bracket is not a directional derivative, okay? Obviously, because both vector fields are differentiated. Directional derivatives by definition is that we are differentiating one vector field. We'll come back to this later on when we give a means to define a directional derivative in differential geometry. Any question about that so far? So we're done with everything about Lie brackets. We know that geometrically they represent a commutation between the flows of two vector fields, and they provide us a means to generate velocity vectors. Sometimes they are new velocity vectors. We'll give the last thing related to differential geometry. So hopefully today is the last lecture about pure differential geometry. Next time we'll see how to apply it to control theory. So one very famous theory or theorem in differential geometry is Frobenius theorem. And hopefully you have seen the video. I'll touch upon something extra here. Frobenius theorem. Any questions so far? So Roger Brocket, these are the things that I don't mention in the very tight course in mechanics. Roger Brocket says the following, that Frobenius theorem to control theory is like Cauchy-Lipschitz theorem to ODEs. What do you mean here? So consider the following problem: x dot equals v of x, differential equation. And I'm putting arrays, so actually x of 0 is some x0 in Rn. Okay? So living in Rn, this is what you see all the time. And the existence question is, does there exist a 1D subset M or N that contains x naught such that V is tangent to M everywhere, right? I mean, the existence, the existence of solution, question about existence of the solutions of the differential equation can be written in this form, right? Any question about that? What's the answer? The answer is given by the Cauchy-Lipschitz theorem about existence of solution, that yes, if V is locally Lipschitz, right? In this case, actually M is just the set of all x's in Rn such that x is the flow along V from some x naught for some time t. So t is smaller than epsilon. Okay? So Frobenius theorem is actually the generalization of this question. Instead of having one vector, we have a bunch of them. So we have V1 up to Vk. These guys, they all vector fields on M. And the question is, so maybe this is an n or m dimension. Maybe these are rank P. Does there exist a p-dimensional subset such that the span of V1 of x, Vk of x spans the tangent space of n at x for all x in n? This is the question. Do you see that this is a generalization of this guy? Any question about that? So yeah, this is the statement of Brock. I mean, this explanation of the statement of Brock is that Frobenius is really essential to control theory in this sense. Okay, so let's see how to answer this question. Obviously, the answer is Frobenius theorem, and if you have seen the lecture, I mean, you're expecting what I'm talking about, and I will just give one of these examples in the lecture and talk about it in more detail. So consider the following example. I have V1 is our usual vector field. So y negative x is 0. This is on R3. I don't see any surface yet. And the vector is defined everywhere. So here is like this. Down there is like that. So it will not be that clear because it's defined everywhere. Here is something like that, whatever. The vector is defined everywhere. So here, for example, is like that. You know? It's defined everywhere. Here is like that. This is the vector. It's defined everywhere. And I have another vector. V2 is defined again everywhere. So this is 0, z and negative y. The vector is defined everywhere. I have two vectors in R3, and I'm asking you, does there exist a 2D surface M in R3 such that V1 and V2 are always tangent to it?